Hello, everyone, and welcome to All Space Considered. Am I being amplified?
Yes. Not much. Who said that?
Not much. How about now? Okay, let me see if that works. Maybe they need to up it a little bit. I think it's in the same place during our Tech. And nonetheless, what a lovely start to this evening's All Space Considered. Thank you all for coming tonight. We are here every first Friday of the month, here to tell you the latest, greatest updates in space and astronomy and exploration. And so, we're glad you made it past the Greek theater tonight. Good laugh. Yeah, for those of you at home, if you drive past the Greek theater on the night there's a concert, it's always a lot of fun. So thank you very much for making your way up here. That's just great. And let me...
It costs $30 to park. What are the prospects for that gondola project?
So there's a question about parking and a gondola and all kinds of things that people have in mind because parking up here is difficult. We're an observatory. We're at the top of a hill and kind of on a little tiny narrow stretch of land, so parking is very difficult. Many have dreamed of a gondola and still do. I used to dream of a zip line because you can see my house. But it's, that's a big engineering feat. It takes a lot of resources. So it's not, to my understanding, anywhere in the current planning. So anyway, I don't know much about parking. That's really I'm the wrong person to ask about that. So I might just move on to a couple of quick announcements. So first, parking's not my specialty. The first is, if you must leave, we ask that you exit out the doors in the back. That leads you to a closet, and that leads you to an emergency exit that we will guide you out through which we will guide you out. No, that's not it either. Out of which we will guide you, should there be an emergency. And so not to worry. I'm sorry?
Even through earthquakes?
You know what? In earthquakes, right here is a great place to be. This is an incredibly solid building, and it would take a whole heck of a lot to bring this building down. As in it's not going to happen. So this is actually the really best place to be. But we'll come back to that later in the show. The other announcement I just wanted to make is you can keep your cell phones on because you won't get any signal here and no one will call. But by the same token, because no signal gets in, no signal gets out, and your phone will be roaming and looking for signal, and you'll lose a lot of battery if you keep it on through the duration of the show. So we recommend airplane or off or something so you'll have all the battery you want to take all your pictures later of sitting next to Einstein and so forth. Okay, two other questions. How many of you are members of Friends of the Observatory? Yay, Friends of the Observatory. That number just continues to go up. I just love it. Friends of the Observatory is Griffith Observatory's partner organization for membership and fundraising. They support so many things here at Griffith Observatory, especially our 5th grade school field trip program. So if you're not a member of Friends of the Observatory, we encourage you to think about it. And if you're not a member and you enjoyed tonight's free program, you could also just drop some little probably not a Benjamin, maybe a Lincoln or something in one of the little bins out there, because I know that Friends of the Observatory would appreciate the contribution. And then lastly, how many are tax-paying citizens of the United States, of the city of Los Angeles? Yay, City of Los Angeles taxpayers, because you make it possible for me to put kibble in my kiddie bowl. We are employees of the City of Los Angeles. Griffith Observatory is owned and operated by the City of Los Angeles Department of Recreation and Parks. You might not know that. We're a city facility, and so we're very, very grateful that you are supporting us and that the city is supporting us and that you're coming up to enjoy the fruits of your investment in Griffith Observatory. Okay, with that, we have one last announcement, and I think this is yours, Bill.
Yes, good. So, welcome, and we do one more thing during the course of the evening, and that is that we play a little game. And the game is called, well, it doesn't really have a name, but it goes like this. We played a bunch of clips of music as you were coming in. All of those pieces of music, songs or movie themes or whatever, are connected in some way thematically to one of the stories that we're going to do this evening. So when that story comes up, it gets introduced, the first person to shout out the name of the song or some identifying feature of the song gets a prize. And if this happens in the first half of the evening, you come down at intermission and collect your prize. If it happens later, you can come down at the end of the show. And the prizes are pretty cool. They're kind of the same thing they've been for a while. We have lots of mission stickers, New Horizons, Europa, Cassini, beautiful Cassini. We have bookmarks. And if I like to say, if you're under the age of 25 and you don't know what a book is, you can Google it. That's what these are used with in conjunction. We do have 2 of these left. This is, if you remember the great mission New Horizons, the spacecraft that zipped by Pluto and another object in the Kuiper Belt and is still on its way out into space. And this is one of these paper models. You punch all the pieces out and you follow the instructions. Did you do it?
Flip it around. Ultimate.
Yeah. I'm glad I did that. And you can make a small model of the spacecraft. And this has all sorts of interesting information on Europa. Anyway, and then we also have calendars. And this is the part that I advance very seriously, although everybody always laughs at me every single time I do this. And it's that these calendars are beautiful. They're produced, a couple by NASA here. These are Mars Exploration Rover's 2-year calendars. We have a bunch of pocket-sized calendars or handbag-sized calendars that are Griffith Observatory oriented. The one flaw that all of these calendars share is that they are all out of date. But you can use calendars again. I'd have to get my phone out for this. I actually have no. All right, you just have to trust me on this. I don't have it. Is it up there? Where is it? Oh, great, thank you. Okay, thank you, Jeff, you saved me here. Is it on here? I'm sorry, I don't want to, oh yeah. Okay, 2015 calendars are good again in 2026. That means that the days and the dates all line up exactly right. Things like, Chinese New Year will probably be off a little bit. 2016 isn't good till 2044, but the calendar is beautiful. 2017, 2023, 2018, 2029. So this, for instance, is 2017 and 2018, so it will be good in 2023. Put it back in your sock drawer, pull it out in 2029. And that's how that works. Now, we have one more thing Jeff is going to pull out, and we have another thing because our guest, I understand, has brought some sort of gifts. Those are mystery gifts, or mystery gift. It may be singular, not plural. I don't know what they are. However, Jeffrey can show you this. Some lovely person in our audience. Yes. If Vanna White ever quits, you're going to have a job. Anyway, and that is the route there and back for Apollo. This was 11 specifically? Yeah, Apollo 11's mission to the moon with all kinds of detail. It's beautiful. I showed it to some of our museum guides, and they all wanted it, but they can't have it because we only have the one. Yeah. Anyway, so that's it. Enjoy. Think about the music you heard. When it comes up, guess it, and you get a prize.
So yes, we look forward to finding out what that mystery gift might be when our guest joins us in just a few minutes. So with that, I think I might just move forward. I want to say one other thing. How many of you either came to or watched online any of our Apollo celebration? Yeah, we had 16 events in 11 days. Yes, 16 events in 11 days. Call us crazy, because we are. And it was great. And the thing I want to say is that I believe that we have the best staff in the world at Griffith Observatory, and they're sitting here or behind the camera or back in the control room. There's another one. In fact, wave, staff. Yay. It was grueling, and they were awesome and are awesome, and we are so grateful to you for all the work you did to make all those programs happen. And we all are still alive to put together an All Space Considered in a week and a half, so that was kind of great. And then the last thing I wanted to say, and I forgot to say, is hello, live stream audience. Why don't we all say hello to the live stream audience? Hello, live stream. So we're glad you joined us, and you were smart not to go to the great. No, I mean, oh wait, no. We'd come up next time. It'll be lovely to have you join us if you're within driving distance. All right. So with those two announcements, today is Friday, August 2nd. As I said, we're always here on the first Friday of every month. And our program tonight I love spicy solar covered in chili. What can I say? Pacific Plate Strikes Back. Uh-oh. Shake, Rattle, and Mole. Then our guest is Matt Kaplan from the Planetary Society. You might have listened to him on Planetary Radio, who's going to talk about sailing on the light of the sun. Big headlines there, very exciting. They can't stop all of us. Does anybody know what that might reference? Yes. Okay. TestCon 1, then the Sky Report, Pretty Pictures, Break. At Break, we play a couple videos. We will turn off the live stream during that period, but we are going to come back to the live stream for part 2 in a rare and new twist. But we're going to do that anyway. We'll see if anybody hangs on through the blank screen for 10 minutes. But in part 2, we're going to talk a little about People Magazine's hottest June of ever. And as I promised in past times when we're talking about how things are changing on the planet, some good news, 1 trillion trees. Spirograph, the solar system, black hole, self-conscious about weird disk. What happens in a black hole stays in a black hole. And one of my favorite ones, Hop Along Elon. Mystery moon mass, too Chandrian, too furious. These guys make these up. Juno's pub crawl, because it's Perijove or PJ21. It's come of age, and it's on a pub crawl around Jupiter. And then Local Void rescues dog from well, which... So let's just move on. That is where I was last month for... What? Oh, you know, I kind of like Ring of Fire for this one, so sure, why not? As if you came to last month's show, you know that I was there with my friend Alpaca, we had a great time. This was just a quick little thing to show you even signs and stuff about it everywhere, even in the gas station here. It's a great deal. You can get Eclipse glasses, coffee, and a croissant for 1,700 pesos. So everywhere you could, there was just so much excitement in Chile about it. That was our little place. You can see up in the upper right the telescopes of Leonard Observatory, the European Southern Observatory. There I am actually at the VLT. In a town called La Serena, there's this wonderful, on the beach, they actually made a sculpture that I'm sure, permanent there. You can sort of see it's all about the eclipse. And then one last little picture from my little Chile trip that I wanted to share, which was this, which is a mace stone for clubbing your enemy. But yeah, nice. But it's pre-Columbian. It was in the pre-Columbian art. But it tells the origin story of the serpent in the sea and the lizard on the land who fought each other. And the serpent kept sending tsunamis into the land, and the lizard raised the mountains in order to stop the tsunamis, and that's basically how Chile got formed, all the tsunamis and earthquakes and tsunamis and earthquakes. So fortunately, while I was in Chile, there were no earthquakes in Chile. But how many of you were here for last All Space Considered? Does this look familiar to you?
We're super safe here, by the way.
I've had a lot of people tell me what a wonderful job Dr. Reitzel did here. Keep everyone calm. And having called him by name, I forgot to introduce ourselves. I knew there was something I forgot. I'm Dr. Laura Danley. I'm the curator of the observatory. Dr. David Reitzel is the astronomical lecturer. Patrick So is the astronomical theater programs manager. Tony is not here tonight, as you can see by the empty chair, our astronomical observer. But Patrick will be covering the Sky Report, so we'll go forward to that. So David, let's flash back a month, and I think one of the things you were most excited about was getting out to see the tracing.
Well, yeah, that's one of the things I was tempted to go run and look at. Was I wanted to run outside and watch the needle go, but I knew that would panic you if I did it. So I think I asked someone, Bill, maybe to go out and check it. So sure, go look at the seismograph. I was checking my phone. We have, anyway, some special abilities in here, and it loaded an earthquake that had happened just moments before the big one, because I was like, it's showing a 5.3. That was way larger than that. The bigger one had not loaded yet. But Bill went out there, and what did we see?
I think it's right here.
There it is. This is after we felt the shaking stop here.
Yeah.
It was still doing that.
So, and it continued with aftershocks for quite a long time, and the folks in here kept seeing the lights go, and the projector was shaking, and it was quite something.
So let's see what our
Okay,
what did our
So here's the actual earthquake trace. There we go. And you're welcome to take a look at this afterwards.
I can tell you I've never seen one so large here. So indeed, there it is. So so let's hear a little bit about what that earthquake did to us here in California.
Okay, so here is a tweet, and there's a before and after picture taken near the earthquake epicenter up just north of Ridgecrest. And actually, the day before, on July 4th, when everyone was celebrating Independence Day, there was an earthquake occurred. We thought that was probably the biggest one. And we can go to the next slide. And this is a kind of intensity map of how it was felt. You can see it from the scaling there. Red is the most intense, extreme shaking, and then it goes down to the bluish parts where it's weak. So it's over kind of a small area out in near the Mojave area. So we thought, well, that's done. But then at 8:19 p.m., while David was doing oil space, we got the 7.1 earthquake, and a quick calculation on that is 5 times stronger than the 6.4, and 10 times more energy was released from it. And it was felt over an extremely wide area, up to 160 miles away from the epicenter. So the kind of shaking you get is, the closer you are, the more extreme the ground shakes. And there's different types of shaking that occur during an earthquake. Since if you're farther away from an earthquake, you normally feel kind of like a run-up, and then the kind of smooth, kind of shaking, rolling vibration. If you're closer to the epicenter, it's a sharp shock and then very violent shaking. So the people up there in Ridgecrest, that's what they felt. So it wasn't a really fun thing to experience.
And it went on
And
just for days and
it
days.
went on, yeah, and we actually felt several aftershocks, and I'm sure you felt several aftershocks from this particular earthquake. And we're going to go to the next image, because this was the day before the 7.1, and then afterwards, right afterwards, a large rupture occurred on the desert floor, and it's about 30 miles long, and you can see kind of before and after.
So we were just impressed that it was in time with this song.
I feel the earth move under my feet. I feel the sky tumbling down.
Now you can see how that road was split, and there was an 8 feet displacement there from this image. And here's another image just taken right after the earthquake had happened and during nightfall. And even though there was displacement like this, there was also displacement kind of vertically. So you can see there's a rise of a few feet there of the ground. And take a look at this stream bed. So the black dotted line represents where the edge of the stream bed is, and this is where it is now, 13 feet displaced over. So it's...
Yeah, they were sitting next to each other, and then suddenly
There was a sudden separation of friends. This is the area that was affected, and of course major damage, electrical poles down, water pipes burst, houses shaking off foundations, and a big large cleanup in several aisles. And also in this area, actually in Nevada, there's a very rare fish called the pupfish, and it's been monitored by cameras, but because it's monitored by cameras, video, they actually suffered the earthquake, so we're going to go and take a look at this. So here's, and look at the time just below. Where is it? Oh, right there. So the shaking starts, and then the water goes. So there's actually, last count was about 100 fish. I don't know how many is left now after the earthquake. But this is a flooded cavern, and the waves were as big as 10 feet.
So a lot of us wondering, why weren't we warned by our ShakeAlert LA? There's an app you can download that the city of LA has provided that's supposed to warn us about earthquakes. Now, it doesn't give you hours of warning. It gives you a few seconds of warning. It senses the shaking off in the distance at anybody's devices that are near it, calculates where it is, and predicts how long it will take to get to you. It's supposed to give folks like surgeons time to put down scalpels so they don't cut people in the wrong spot. Bring transportation systems to a halt. You don't want to be in a subway going 60 miles an hour in a tunnel when an earthquake hits. It'd be kind of good to shut it down. Well, nobody got an alert at all. And it's because, well, ShakeAlert for the past 2 earthquakes. Anybody get this? No.
Oh, they said you'd all get it.
Okay, good. As long as we make one person happy, we're good.
That's our motto.
It is. So, but this is sort of the strength of the shaking that you feel. This isn't the magnitude, the Richter scale that you're used to. This is the CIIM intensity, of course. But 1, you don't feel it. 2, felt by a few. All the way up to 5, felt by nearly, frightens a few. That's where they drew the line. They just frightening a few wasn't good enough for the city of LA to warn us. They want to frighten, if it's frightening many or people move unsteadily, then they feel you need to know. If you're just a little bit frightened and you're still steady on your feet, they figured that's where they would draw the line. However, folks complained, and there is talk about making adjustments to it. So we'll get back to you if we hear about that. Now,
About 10?
the scientists have this one.
Oh, 5.7.
So it sensed it near it, and those rings coming away from it are traveling to LA. This scientist is in Pasadena. She's a earthquake scientist.
Saying 5.7 with 26
Yeah, that's
seconds.
Lucy
Yes,
Jones.
The one that was a 4.9,
And
we
here it
felt.
comes.
So this, assuming that the magnitude isn't really misestimated, my guess will be we'll feel this as it comes through. In about 12 seconds.
10
Here it
seconds.
Do we
comes.
expect this magnitude of aftershocks throughout the rest of the evening?
Well, yeah, the largest aftershock is likely to be a 6.
Let's wait, here we go.
We should be feeling it now.
No?
Very,
There it is.
There it is.
So some of the folks felt it.
yeah.
That was the phone ringing.
Yeah, so
I felt the one that was labeled 0.9,
so the question, of course, is will they let us have that system where we can adjust it and say, well, I want to know about very mild shaking, and somebody else might only want to know about the strong shaking. I doubt they'll let us have that, but maybe they'll let an astrophysicist have it. I don't know. I need to send some emails.
So if you don't have the real-time thing after you feel the shaking, you can go to the USGS website and see what's shaken today. This is actually taken today, so you can see the Chile in orange and the Indonesia earthquake, large circles. It's red if it's happened in the last hour, orange if it's happened in the last day. Oh, presaging, very good. And this is just those above 2.5. This is all of them. And there is the website. So if I have it actually on my phone always. And I mean, I feel the teeniest little bump and I go to see, was that an earthquake? So it's kind of handy if you like to find out after the fact what's going on. So indeed, you do notice a pattern that the Pacific Basin is surrounded by these red fault lines, which is referred to as the Ring of Fire. And so we thought, in addition to all the earthquakes, we'd give you a short Ring of Fire roundup. Oh. Okay, it's supposed to go. So it turns out, we didn't know this, but there's a volcano live site you can go to as well by the Smithsonian, so you can find out your latest volcanic eruptions, and this is recent. again, is tracing out the Ring of Fire. The Ring of Fire, by the way, is because the Pacific plate, the plate tectonics, the movement of the plates of Earth's crust is grinding against the neighboring plates, in our case, against the North American plate. And so you get this kind of occasional slipping, which gives you the earthquakes, or you can get underneath it, there are molten magma, what's the word I want? Not residue, reservoirs that will occasionally come up through the cracks in the plates and give us the earthquakes. So there were 3 spectacular earthquakes just in the past week. Here they are, details of them. I'm not going to even try to pronounce them. But there was one in Peru. This is kind of a cool. Listen to that sound. A big eruption there. And this one in Indonesia is a particularly fun video. A bunch of people watching.
Oh my god, oh my god, oh my god.
You feel kind of sad laughing because, because of interest of time, we trimmed it. But they were actually standing there watching it erupt for quite some time before they decided to run. So that was smart that they decided to get out of there. Earth isn't the only place that has quakes. So, David, you want to tell us about another world of quakes?
Yeah, Mars has Marsquakes, we've learned. We sent this lander, the InSight lander, to Mars, and it landed there. And it deployed an instrument called the SEIS instrument, and they covered it with a wind shield and a thermal shield so that wind and things wouldn't shake it. But we do think that Mars has quakes, and some folks created some simulations showing what those quakes might look like as they traveled through there. That's the artistic representation of it. But what's happening there is there's 2 different kinds of earthquakes, or 2 different kinds of waves associated with the earthquakes. P and S waves. The P sort of primary, S wave secondary. I've heard them said really has to do with sort of the way the ground shakes. One is more of a pressure wave, and one is more of a longitudinal wave. It actually shakes up and down and side to side. That aside, some of them, the P waves can travel through a liquid core, the S waves cannot, and they also change their direction and refract and bounce off of the different layers, so you can learn about the internal structure of a planet by studying the earthquake waves. Now, first question, however, is how do the Marsquakes compare to basic earthquakes, but also to moonquakes? The Apollo astronauts left behind seismographs on the moon's surface, and we were able to pick up moonquakes. Some folks thought, well, best way to do this is to experience them, some researchers in Switzerland, and they have a room that shakes according to what an earthquake would do. So first they were going to experience what an earthquake would be like, and then a moonquake, and then finally the Marsquake, and we'll see how they differ. So, well, first this is just about the earthquakes bouncing off the insides. I've had a blank picture there, and I was confused. But anyway, I already talked about that. So let's do the shaking.
This quake, we'll start with the P wave, that you feel there. And then in a few seconds, we'll hear the S wave arrival. Slightly bigger.
So they thought that was kind of fun. Now let's
Next
do moon.
thing is one step more exotic, which is the moon. This is the SP recording. So this is slowly getting bigger.
They started to look a little more worried there.
Next thing we'll load into the system are the Marsquakes. We want to know how they feel on the scale between the Earth on one side and the Moon on the other side.
So now they amplified that 10 million times, the moon 1 million times, and they could have scaled it down, but notice it seemed to be a little bit more rolling. There was more rolling action in the Marsquake. Well, the analysis they did on what was seen was that the moon's surface is very fractured. It's fractured fairly deep. The moonquakes have trouble passing through that, so it affects the signal. On Earth, we have less fractures, although we do have, of course, these plates that are grinding against one another causing all this. But overall, the structure is a little bit more solid and the earthquakes can travel through it. It turned out Mars was literally in between the two, just like on this picture. It's a little bit more like the moon than the Earth, but it's more, compared to the moon, it's more Earth-like. So it's in between the two, the earthquakes that they were to pick up. And that video, we happen to notice they do show a clock in there. We edited it out, but I love their clock. Time for a Mars quake. So they're ready for it at any time. Now, InSight does have another instrument that, in addition to a weather station that we'll talk about, it has an instrument called the HP3, and also known as the mole. And the mole is supposed to dig down into Mars and measure the heat flow, how heat is transferred through the soil. It's an important measurement you can make to learn a lot about the soil. It got stuck, as you can see, and they thought, kind of in that angle, that's the mole, they removed the cover. So they thought, well, we'll take the little scoop and we'll go down next to it and we'll push on the dirt next to it. And that's their first test, to push it, and they're going to go down there and seed it and hopefully provide the mole a little more friction to pull itself down through the soil. So this is the first attempt to try and get the mole working again, because it failed. It only went, as you can see, a handful of centimeters down in there, which was unfortunate. And finally, like I said, our weather report from Elysium Planitia, InSight's taking daily weather measurements, and on Sol 233, the high was minus 14 degrees Fahrenheit, and the low minus 146 Fahrenheit. And again, the air pressure is about 1% of Earth's. So it's mostly carbon dioxide.
All right, so we are very excited this week of all weeks, and in fact we invited him to be our guest this week before their big announcement, so how lucky were we to have joining us tonight Matt Kaplan from the Planetary Society. Sail away, everybody. I couldn't even hear who said sail away first. If you think you were in the first person, come on down, get a prize. So with that, can I ask Matt to come join us? And there's your clicker.
Great.
So Matt, tell us all about this.
Well, we're thrilled. We're very proud. We had a very happy staff meeting today. But can I say, first of all, how happy I am to be here?
Oh.
Because as I have told you, I grew up here at Griffith Observatory. Not here because, as I said earlier, this was all dirt. But up there, before I could walk, my parents were bringing me here. So, I mean, I have to, wait a minute, if I can reach it. I have to complete the outfit. I feel a little odd because normally I'd be wearing a space tie, but I had to wear the Lightsail shirt.
Yes, you did.
Yeah. And I have a cheat sheet. Should I just start going into
Sure,
this? Yeah.
please.
So to get started, that is Lightsail. And this is the first full resolution image that we got during deployment. The sail is actually not fully deployed at that point, and it's a fisheye lens, so this is kind of corrected. There's been some Photoshop fun here to clean it up a little bit, but isn't that spectacular? And anybody can name that landform that we're sailing about? That's right. So Lightsail has a history that goes back about 10 years, but really we go back about 20 years. Because we attempted to fly the very first solar sail ever 20 years ago, well, almost 20 years ago, when we flew Cosmos 1. And it was a huge spacecraft compared to this one. We had high hopes, but unfortunately, because we could only afford a former Russian or Soviet submarine-launched ICBM, because they gave us a deal. The deal was that we went straight into the Caspian Sea. So we never got to find out. And that's when we went back to the drawing board and came up with what you see here. We've got a little, it's really just sort of a thumbnail style approach, but if this works, you'll actually see the sail being deployed, which is pretty cool. So as this happened, I had been at the launch with a lot of our folks at the Kennedy Space Center, which you'll see some pictures of soon. But for this, I was at our mission control, which was right up the coast, excuse me, at Cal Poly San Luis Obispo. Here's a picture of our mission control room. Yeah, right. Apollo 11. Here's our control room. And there really are only 6 people sitting at laptops like this one who were controlling a spacecraft in space. Some of the other folks there were other team members who worked on this, and if you look carefully, you can see the youngest member, 3 years old, who is the daughter of one of the primary team members. So we had a good time up at Cal Poly. Here's the boss. He couldn't be with us. You may know Bill Nye. Might have heard of him, the science guy. He's our CEO, Chief Executive Officer. And he couldn't be with us except virtually, so here he is by Skype.
With a broken
celebrating
wrist,
with
it
us.
appears.
I don't know what he did. I didn't get to ask him, even though you can see my watch on the left there because I'm standing just off screen. Here I am about a month, actually 2 months before launch, in the clean room at Cal Poly. I'm a radio person, so I rarely take off my headphones. And there is Lightsail on the table. I should be pointing here. Going into the P-pod, which is the little thing that has a spring that actually ejects a CubeSat. I don't know how many of you are familiar with the concept of solar sailing, but it's a much older concept than a lot of people realize. And this, I hope this isn't too hard to read up there. It starts up at the top, 1608, with Kepler. And there is one step missing here at the beginning of at the turn of the 20th century, because that amazing guy, Konstantin Tsiolkovsky, was actually the first person to figure out how this might actually work. And he pretty much worked it all out and did a terrific job. We do it pretty much exactly the way he expected it to be done.
So how does it work? How do you get anywhere?
Well, we're coming to that.
Okay.
But it's surprises a lot of people that light can do the job. It's not the solar wind, as a lot of people suspect. It's the actual photons from the sun. And more about that in a moment. There is the spacecraft. How many of you are familiar with CubeSats? Great little format. There are literally thousands of these, either in space or in development, or at least planned by groups as, low level as high schools. A lot of these go through Cal Poly, because Cal Poly and Stanford invented this format for a spacecraft that's based on 10 centimeter by 10 centimeter by 10 centimeter cubes. We have a 3-unit one, so it's about the size of a loaf of bread, roughly 10 by 10 by 30 centimeters. And you're seeing it here with the solar panels deployed, which are probably pretty obvious there, but up there is one of the cameras. And there it is, we have two 2 megabyte, so not too impressive, but cameras that were able to deliver pretty good photos. And we're still downloading those images. We get thumbnails, and then we have to decide which ones we really want to, take up a lot of time as we pass over a ground station and work with. Here is the sail, stowed away. And that becomes this. So our little 10 centimeter wide spacecraft becomes a 5.6 meter wide solar sail. Think of, roughly the size of a boxing ring, as it says there. And it's just made out of silverized mylar. It's pretty cheap stuff. It's ripstop, like if you've got a good tent that's made out of ripstop nylon. It's the same stuff in case it gets, perforated by a micrometeoroid. It hopefully won't tear too far, or space junk, which is maybe more likely. And so far, so good. Here is a shot of our control panel, or mission control, that anybody can access at our site. You can just go to planetary.org or sail.planetary.org if you want to skip our homepage. And you can monitor where it is. You can also on here catch passes of Lightsail as it may be going over your head. Because now that the sail has been deployed, it's big enough, if you catch it near dusk or dawn, you might be able to see it go over you in the sky. So we're up there with the ISS, although on a much smaller budget. Like I said, I was at the launch, and here is an amazing photo of people at Kennedy Space Center. It's lovely to see these faces, but what's really amazing about this is that what you're seeing is entirely the light of the rocket, except for a little bit of help from a big moon and a few stars. It was pitch black there because they turned off all the lights at KSC, so we did have some moonlight, but this is the light of the Falcon Heavy being launched. And of course, we were not the main payload on this.
The Falcon Heavy for your CubeSat, yeah.
Kind of overkill. But there were about more than 25 payloads, and the main one was an Air Force one that we're not allowed to talk about. And it was absolutely spectacular. It didn't happen until about 2:30 in the morning. And yet, by that time, we were all wide awake again because it was just thrilling. And this is actually now being called a rocket nebula or launch nebula. Doesn't it look like an astronomical thing? What you're looking at there, the upper portion of the image up here, that is the backlit portion of the two boosters, the side boosters on the Falcon Heavy, after they've separated, but they're still surrounded by a lot of the exhaust gases. And then below that, you're actually seeing the center core stage with that beautiful image. And if you can count that there were nine engines still going there because it's basically now a Falcon 9. You have strapped 3 Falcon 9s together for stages, and you got 27 big rocket engines going up into space. This later image from the mission, as I said, we're hoping to get a lot more of these. This may help you put yourself in the image. And as I said, you can catch us right here at sail.planetary.org. To answer your question, because I'm done with slides now, it's true photons don't have mass, as you guys know, but they have momentum. And that momentum, when they strike something, shiny especially, they can impart that momentum in actually 2 ways. They impart that momentum to that shiny thing or anything, and that's what's allowing us to raise the orbit. We only this week declared success officially on Wednesday of Lightsail because our goal was to raise the apogee, the high point of that ellipse that it is currently in, going round and round the Earth about every 100 minutes. It's up about 700 kilometers because we had to get above most of the atmosphere to get rid of the atmospheric drag. Still a little bit of air up there. And we've been able to do that. So far, we've raised the apogee about 2 kilometers. And we spend about 2/3 of our time solar sailing and about 1/3 detumbling, as we say. And I could go into more detail. It's
Well,
fascinating.
I've got to ask what detumbling is. I saw it on your page there too, so I was wondering, what is detumble?
Sure. We have a big reaction wheel. Well, not that big. And boy, was it expensive. I can tell you these things cost a lot. Reaction wheel is just a flywheel inside the spacecraft. A lot of spacecraft have 3, so they can change X, Y, Z. We only needed it to change 1 axis. And that's because as we go around the Earth, and this is the big first that we did, other than doing it from a CubeSat, we have to change twice during each orbit, because when we're flying into the sun, we don't want to have those photons hitting the sail full on. We want to be edge on to the sun. But when we get around the orbit to where the sun is behind the sail, manner of speaking, then of course we want to be able to pick up those photons and accelerate. So that's what the reaction wheel does, because it has to do it fast. But, sorry?
You're tacking and jiving.
Exactly. We know how to tack, because you can tack into the wind just like people do offshore here. And we also, but the reaction wheel, as you use it, it just spins up to a certain speed and then it can't spin any faster. So we have to do other stuff to stop it and reorient the spacecraft. And we have the other way we orient the spacecraft. This is so cool. We didn't invent this. They're called torque rods. And they're little things, they're only about as long as your finger, but they're basically electromagnets. They use the Earth's magnetic field to slowly change the orientation of the spacecraft. And that's how we do the detumbling while we're getting the reaction wheel back down to 0 so that we can start up again. It's amazing how much technology it takes to make even a little tiny guy like this hang out in space for a while.
So you said it goes back 20 years to when you first started doing it. For this particular project, when did you start bending metal? When did you start building the craft?
Well, Lightsail development began about 10 years ago. a lot of the initial design, which is still there, was done by a local company called Stellar, and I think they started the actual bending metal quite a while ago, like 7, 8 years ago. But we had a lot of challenges trying to pull this together. Back then, CubeSats were still pretty new, and nobody had done anything like what we're doing with solar sailing. So there was a lot to work out. And there were times when we thought that we just weren't going to make it. We were going to have to give up. But we brought in some great new people and some really innovative thinking at some other places, like a company called Ecliptic, and a lot of other great folks who just wanted to see this happen because of this wonderful, romantic, and yet incredibly useful form of propulsion. And first we did Lightsail 1 4 years ago, which was just a test. Because it only went up high enough, it was in too much atmosphere. We were able to deploy, but the air was too thick and it came down in a week. We knew that would happen. We had to wait until we could get a free ride from a Falcon Heavy to get up to this, not low Earth orbit, but mid-Earth orbit, to really be able to sail on the light of the sun.
Now, this is, of course, technologically fascinating because solar sailing is something that a lot of people have been talking about for a long time. But I want to focus for a second on the organization, because this isn't NASA that did it. It's not the Europeans, it's not even SpaceX. So tell us about the relationship between the Planetary Society, that you are where you work, and this project. How did it come about, and who paid for it?
Well, you paid for it, if you're a member of the Planetary Society. Do we have any members of our group here? Thanks. Thank you very much. You should, of course, be a friend of the observatory as well.
That's right. We have a totally symbiotic mission here.
It's a Venn diagram that's almost a circle.
Yeah.
You members and a lot of other donors. We had a few major donors, one who remains anonymous, who really made this happen. But you know, you're looking at something we are told that if it had been done by a major space agency, would have cost 20 times as much. So the whole project for us was about $7 million end to end. So think 140 if it had been done elsewhere. And that was entirely crowdsourced. There was no money from NASA, no corporate support or anything like that. Just a lot of people who were captured by the romance and the practical advantages for the future of what this kind of technology might be able to do within our solar system and maybe beyond our solar system.
Oh, say a word about that. I have one more question, then I'll throw it open to the audience. But why is this important for beyond the solar system?
Well, it's key that we call this light sailing. In fact, the guy who really ought to be here is our program manager, my colleague Bruce Betts, our chief scientist. He is in Aachen, Germany right now at the International Solar Sailing Symposium, which next time they hold it, they're going to change it to, I think, the International Light Sailing Symposium, because there is the thinking that rather than using the sun, which is great in a lot of the solar system, and it's a perfect application for doing things like monitoring solar weather and looking for asteroids with an infrared telescope, because you don't need to carry your own gas along with you. But you may have heard of, I'm sure you guys have, of the Breakthrough Starshot project. Breakthrough Starshot is the idea that we could take small light sails, even smaller than ours, maybe just a meter across, and launch them, and then hit them with humongous lasers for just a few minutes, and accelerate them to, the current thinking is to as much as 30% of the speed of light. Pretty cool. So think about it. You could get to some place like Alpha or Proxima Centauri in 12 years, maybe. 12, 13, 14, 15
You could do
years.
the Kessel Run in 13
Good job. Yeah. Take that, Millennium Falcon. Got nothing on us. Now, we got a long ways to go, because at this point, they still can't figure out how to vaporize the sail when they hit it with the lasers. So materials science is going to be a big part of this. You can't slow down, although Robert Forward did come up with a way to do that, kind of a double sail system. And, electronics that might weigh just a few grams in the middle to transmit back to Earth. Anyway, they're thinking this may be practical, but we're talking way down the line.
Yeah, but once you get to Alpha Centauri, then you use its starlight. You need to have it optimized in red, but, you know, to slow things down. Okay, you laughed.
it's
Is that
incredibly
impossible?
exciting. Well, they have talked about, yes, using other stars
Yeah,
to
because
help
you got to bounce from
decelerate
star
it.
to star.
And even like swinging in really close to the star to do not a gravity assist, but sort of a gravity brake. So yeah, it's possible. But forward's concept, it's too bad I don't have a slide of it. It's really pretty cool. It's like a central portion of the sail separates and reflects back on the ring that is left and from the other side
Oh,
and,
cool.
and slows down the sail. He was
Smart.
He was a smart guy. Anyway, so that's some of the potential.
So are there questions out there before I monopolize them completely? Yes.
What is the next step?
Well, we have no plans for Lightsail 3. What we're going to do is now, this is technology that we hope will inspire and will be transferred to lots of other folks. We got a lot of praise from all over. Thomas Zurbuchen in NASA, the head of space science in NASA, just said what a great proof of concept and talked about all the potential for this kind of technology. The next thing we're going to do that'll be similar is we're going to have a competition that won't happen until next year to pick technologies that we want to support. And so we're going to look to you folks and other people around the world, it'll be international, to try and come up with the next thing. But we want somebody else to build Lightsail 3.
Yes.
I thought I saw some really small acceleration value, and do you have a reference for the nanonewtons of thrust, or what? What do you got there?
Somebody does the real numbers. The most I can tell you is there are two ways people often describe it, and one is that much, one piece of paper, or the weight of a fly. So it's somewhere between the two of those, I would guess. Yeah, it's not bad. Well, and we weren't the first to solar sail. Icaros, wonderful solar sail project from the Japanese Space Agency, very innovative, actually used LCD panels to orient the spacecraft that would turn on and off. Brilliant mission that went to Venus. They didn't have to orbit and change the orientation like we do, twice in orbit. And we actually have a higher coefficient of acceleration than they do because of the mass of our spacecraft and the photon catching capability of our sail, that proportion, ratio. Yeah, that's how I've heard it described anyway, by the boss. He's the science guy, he ought to know.
Yes.
What's happening with the satellite now? What's the lifespan?
Can you repeat the question?
Sure. The question was, what's happening with Lightsail 2 right now? It basically automatically, autonomously reorients itself each orbit, but we have people who are still at this point around the clock, monitoring, keeping track of what's going on. Up at Cal Poly, we have 4 ground stations around the world, so we can't really monitor it all the time. It has to be somewhat autonomous. We hope to continue actively raising the orbit for about a month. But because we only have control of one axis, we actually, as we raise the apogee, the high point, the perigee is lowered. And so eventually we're going to be caught by the atmosphere, and we're going to crash. We're going to be burned up. That's what will happen. And we have maybe a year, though, if we're lucky, that we'll be able to keep orbiting. But definitely for another month, we're going to be actively trying to raise the orbit.
Next question, yes.
How were you able to confirm that the momentum transfers by photons and not solar wind?
Well, there actually is. We do take the solar wind into account. And it's just a small fraction of what we get from the solar wind. And we know that just because we know a lot about solar radiation at Earth orbit and the flux of the solar wind. So we're able to factor both of those. But really, it's interesting. You wouldn't expect this, but the light of the sun dwarfs the effect of the solar wind.
Why can't you raise the perigee as well?
I'm no expert on this in celestial mechanics, and I've never read the Principia, But it does have to do with our inability to do fast reorientation of the spacecraft. The torque rods are cool, but they can't change it quickly. And we do only have really gross control on one axis. And I'm told that's why we can't do the perigee as well.
Okay, well, we have time for one more question.
I was just going to ask, you guys don't have any other means of propulsion other than the solar sails, but is it a possibility going forward to include solar sailing and other means of propulsion kind of coupled together?
That is such a great question, which I wouldn't have had a good answer for until this morning. There is, first of all, NASA, we knew had a project called NEA Scout, Near Earth Asteroid Scout, which will be a solar sail. And we've been working really closely with them on that solar sail project. But just this morning, I heard about a project that NASA's also working on, very early stages of development, that is a solar sail, but the sail, in addition to catching sunlight, is actually a thin film solar panel. And that thin film solar panel will run an electric engine, an ion engine essentially. And so it will have both forms of propulsion. And so that's incredibly cool.
So we can explore the asteroid belt with a hybrid.
Yes,
In a hybrid.
yeah, it's a hybrid.
Yeah.
Like the one I drive, it's a hybrid.
That's right.
Exactly
Just
right.
like the one you drive.
Yeah.
Right, my
I wish-
other car is a solar sail. Right?
Mine's kind of solar powered, but it doesn't carry it with it.
Yeah.
So anyway.
Well, I'm going to ask you to stay up here because we have
Thank you.
two more
Sure.
stories, and I want your comment on them. But let's thank Matt for his wonderful presentation.
Thank you.
And you will know why I would like him to stay up here, if it's partially for protection, but that's because we're going to go into a dangerous territory here, and that is... Dun, dun, dun. They can't stop all of us. So Jeff is going to tell us about this.
Hi. So how many of you have heard of this thing? Yeah? Yeah?
Unanimous.
How many of you are going to this thing? All right. So for those of you who don't know, I do have a little bit of history for you. I want to talk about Area 51. And the most important thing... ooh, can I have a clicker?
You can have a clicker.
All right. All right.
Power.
The most important thing to know about Area 51 is that Area 51 does not exist. And I don't mean that in like a spooky government's keeping secrets way. I mean, it's not actually called Area 51. The source of the name Area 51, the only time it's been called that was a 1966-1967 CIA document talking about where they were launching spy planes out of to fly over Vietnam. Its actual name is really cute. It's Homey Airport, also known as Groom Lake because that's the name of the dry lake that the airstrip is built on. Its existence is not a well-kept secret. It clearly exists. It's right there. I can see it on Google Earth. The Google people even made cute little 3D models of the buildings that are there, little warehouses and that. And there's actually a plane that flies out of Vegas to the Nellis Air Force Base facilities where the Area 51 is located, called Janet Airlines. And what is you're saying, Janet?
Oh, yeah, it stands for just another non-existent terminal.
Yeah. And so they actually have a 737 that takes them to work on a daily basis. Now, until I think it was 2014, what they were doing there was classified. But since a Freedom of Information Act request came in, we found that it's been really heavily involved in the development of spy planes and stealth aircraft, as well as the testing of captured MiG fighters during the Cold War. Now, because there was a total information blackout on what it was that they were doing there, conspiracy theorists did the thing that they always do when they don't know what's going on, and that is aliens. It's aliens time, guys. Let's go.
What happened to Doge?
Alien Doge up there. So here's the thing. This conspiracy theory is the source of this Facebook event. If we scroll down past the 2 million people who claim to be going, we'll get the details, the description of the event. We will all meet up at the Area 51 Alien Center tourist attraction and coordinate our entry. If we Naruto run, we can move faster than their bullets. Let's see them aliens. So, let's see them aliens is a pretty self-descriptive one. The rest of it kind of needs a little unpacking here. For those of you who did not grow up at the same time as me, you might not know what Naruto running is. And if, well, here it is. It's based on an anime where you run with your arms flailing behind you. The joke is it makes you go faster. It doesn't. So while you hear the name of the event, and you might imagine, oh yeah, Storm Area 51, you expect something like this, beautiful and majestic charge. No, you get this. Oh, and you just wait. I got footage of real people doing this. It's wonderful. So yeah, just imagine a whole bunch of people in the desert. Like this, running around. So, yeah, it kind of speaks for itself. So because so many people have signed up to do this, the Air Force has actually responded to this event. They have an official response. Basically, in summary, we're an Air Force base. We do live testing. There's like a bombing range right there. Please, please, do not do this. It is a terrible idea. And the guy who made the event didn't actually expect it to get this big. He wrote the Air Force saying, oh, hey, this is a joke. My favorite part is, I just did it for the thumbsy uppies on the internet. And we also want to be very clear. All Space Considered says this is a very bad idea. Don't do it. So even though it's a really bad idea, hopefully nobody actually tries to storm Area 51. But at the very least, we got some really good memes out of this whole thing. Just do a Google search for Area 51 memes. It's so good. So yeah. So how many of you are free on the 20th? The 3 a.m. though, that's kind of the deal breaker for me. Yeah. So that's what's happening.
Not breaking into a government facility.
Not breaking into
That's
a government facility. So if you see this running around, if you've seen a resurgence in Area 51 memes and interest, it's this guy's fault. Thank you.
So, any comment, Matt?
I've been to Roswell. I think this has been put on by the Roswell Chamber of Commerce because the whole economy there is based on Area 51. Yeah. They do sell some pretty good alien jerky, though. I don't know if it's made of aliens, but it's good jerky.
So, on to something real.
Well, we've been looking for the planets that the aliens have come from. We haven't figured that out quite yet, but in all honesty, this is a satellite that is up there, a telescope looking for exoplanets. It's the Transiting Exoplanet Survey Satellite, and it's been in action for a year. Believe it or not, it uses the transit method, stares at stars, it waits for their brightness to change by a small amount. The bigger the planet, the bigger the change in brightness. You can tell the size of the exoplanet, as they're called around other stars, off this method. Now, here was the plan. It was looking at the southern hemisphere. Notice the South Pole gets extra observations. It's continuously observed. The rest of the panels are kind of observed in segments. And the North Pole is going to get a lot of coverage. Well, it has completed the southern observations already, and you can see them unwrapping here. It's fun to watch the Milky Way show up, and that is the Large Magellanic Cloud at the South Pole there. So it has finished the south, and it's moving on to the north. And the exciting news is it keeps finding more exoplanets. I talked about some of them last show, and here's some more that it just found. Earth is there as a reference, of course, but it found a small planet that's not much bigger than Earth. It's only 1.2 times the radius of Earth's. However, it's probably rocky, but it's in a 3.4-day orbit around its star, which means it's super close, so 400 degrees Fahrenheit, that's kind of toasty. There's two other planets in this system. We'll take a look at kind of the close-ups here. There's two other planets in the system that are a little bit more like, well, they're in between the size of Earth and Neptune, so they're in kind of a weird gap where we don't see a lot of exoplanets of that size. So why these two were there in that strange size of 2.5 Earth radii or so, remains to be answered, but neat that TESS is picking them up. 2 more were just announced, although the first one was a TESS exoplanet, the closest one in there, and it orbits in like 5 days, and it's super hot. It's, again, hundreds of degrees Fahrenheit. The second one out is also too warm to have liquid water on the surface, but that blue sort of torus out there, that blue donut, is the range where you might have liquid water on the surface on a planet. So that last one, GJ357d, such catchy names, it's actually in that zone where it might have liquid water on the surface. But it's, again, around 2 times the size of Earth. It has a mass something, it's about half the mass of Neptune. Take that back. It's less than that. In any case, I think it's going to have a thick atmosphere, probably too thick to have life. But still, it's in the habitable zone, and if things went just right for it, maybe there's liquid water on the surface there. There was a TESSCon going on this week, so more and more test results kept coming out, and a postdoc that was attending it created an orrery, a lot like those Kepler telescope orreries we were seeing. And this one's kind of neat. Our solar system is in the center there, and that is Mercury, Venus, Earth, and Mars, their orbits to size. And these are all the double planet systems that TESS has seen. Now notice, most of these planets are super close to their star, and that's because TESS has only been observing for a year. You need to watch a planet go around multiple times to confirm its existence. So if it's only observing some of these segments for short periods of time, and the southern region continuously for a year, and then the north continuously for a year, it's going to take several observations to go back to get planets that are far from their star. But still an exciting time to see TESS starting to give us exciting results like this. So they're really coming together.
Okay, and one little short thing, just in case you heard it in the news. We're all safe, but there was an asteroid that came about 14,000 miles away from Earth. I think I have that, 40,000, pardon me, big difference. 40,000 miles away from Earth, but still inside the distance to the moon, which is 238,000 miles. So just here's a little video showing you the, there we go, whee! But it didn't hit us, happily. It just whizzed past us. But the reason this was in the news was because it wasn't, while it was discovered last year, people didn't have the orbital information about it, so we didn't know it was coming. And nobody likes a surprise asteroid that's large enough to, it was about 437 feet by about 128 feet. I think those were the numbers. Anyway, large enough that if it had hit a city, let's not say Los Angeles, some city, other city, it would be enough to take that to, not funny. Sorry, he just named a city. One I used to live in, and so I'm not liking it. But anyway, the good news is it didn't hit. It did not hit us. But
let it hit Tunguska again.
Yeah, right. We did have a story a couple of months ago about how often Siberia does seem to get struck. Right. Anyway, or have big fireballs that come in. But anyway, not to worry, but it does argue, and in one of the articles that I was reading about it, I actually saw that there was a recent poll that said that the public would actually very much like to see us spend resources in NASA on understanding asteroids and figuring out ways to mitigate a possible asteroid strike on Earth. So I think that's just something to bear in mind, and hear that, NASA? Okay, last thing for the evening before pretty pictures and break, and then we'll come back the second half, is the sky report. So Patrick, who is not Tony.
Yes, right, that's right. What's in store for us in the night sky this month? Well, if you plan to go out camping in a dark area, and if you want to get ahead of the crowds, and camp out, say somewhere near Area 51, the skies are nice and dark, and you can actually see this beautiful band of light called the Milky Way, and this is a kind of a wide-angle view of the sky, showing the Milky Way sweeping between 3 bright stars, Deneb, Vega, and Altair, making a summer triangle, and then sweeping down to the brightest portion of the Milky Way, which is representing the center of our galaxy, near Sagittarius and Scorpius. And each of these constellations has a bright planet near it. The brightest one is Jupiter, and a little bit fainter is Saturn. Now, if you can't find either of these planets, this next one graphic will help you, because on the 9th of August, the moon will be right next to Jupiter and just above the bright reddish star Antares in the heart of the Scorpion. And then just 2 days later, the moon will move over to Saturn.
Right.
So
With a big
Saturn is a lot
pointer.
fainter, but it's right next to the moon, so you might have a hard time seeing it, but it's right there. So what would you see if you had a fairly large telescope? So say a 14-inch telescope. This is an image from an amateur astronomer showing Jupiter and its bands and this beautiful, the Great Red Spot, which has darkened, so you can even see it through an even smaller telescope, something like a 60-millimeter telescope or a 2.5-inch telescope in aperture. And Saturn, its rings are wide open, and you can see that fairly easily even with a small telescope. And if you don't have a large telescope or even moderate-sized telescope, you can always come on by and at night when it's clear and look through our telescopes on the lawn and even on the roof, and you can see both these planets. They're being featured through our telescopes at this time. In the morning sky, there are no bright planets or anything like that, but you can. My favorite thing is to look over towards the east and watch the constellation of Orion emerging from the dawn light of the east. It's kind of like the heliacal rising, the rising of Orion when you haven't seen it for a year. So that's kind of beautiful to look at.
That's actually my least favorite. I love you as one of your favorites, least favorite, because that means fall is coming.
Oh, well, yeah.
So whenever you finally see Orion and you haven't seen it all summer long, then you, uh-oh.
Yeah. Okay, well, how about the constellation Taurus? You like that?
Yeah.
That's just above that. And then the beautiful cluster of stars known as the Pleiades or the Seven Sisters. It's also worth looking at in the morning. Now we're going to go to our moon calendar. And so the early part this month, first week, is great for the Milky Way viewing. And then the moon gets brighter and brighter until it's full on the 15th. And then it wanes again, and then you can, at the end of the month, it gets dark enough to see the Milky Way. But the few days leading up to the full moon, in fact, on the 13th, 12th and 13th, that's the night of the Perseid meteor shower. And so its maximum is the night of the 12th through the morning of the 13th. You do have a small window of a moonless sky, and if you were to look on 9th through 10th, you have about 2 hours after moon sets and before dawn, 1 hour, 11th through 12th, and less than 20 minutes on the 12th and the 13th, which is the maximum. So it produces about 80 to 100 meteors in a clear, dark sky. Here with the moon, you'll probably see a few bright fireballs and a few bright meteors. Per hour, yes.
So this is the time we go to pretty pictures. So the first pretty picture is of our speaker next month. part 2. And thank you for staying. I know that those of you who pay for parking, it's quite a deal for you guys to do that, and I'm very grateful. Thank you so much for staying. So we're going to start the second half with a little bit of news about Earth. And if you've been watching, you are aware that we've had a really, really hot month of June. This was the June information, even though we're now on the 1st of August. The report always comes out in the following month, so we'll hear in August how July went. But it was the hottest June on record. So of all the Junes that have ever been measured, it was the hottest one. So you can see the distribution of where it was hot, and in particular, the United States kind of did okay. It was a little cooler in the United States in June. Europe, not so much. Very, very hot in Europe, and very hot if you look in the northern regions up by Siberia. And so there are several things that are results of this, and we're going to talk about them. And this continued, of course, into July. But we just saw absolutely record heat in France and in Europe. Breaking records everywhere. More records broken today, by the way, in Paris and in London. So, of course, the French had to look very fashionable while cooling off at the Eiffel Tower, as they always do. But there were a lot of sort of climate, or I should say, a lot of weather extremes during the month of June. So you can see basically a lot of those little red ones are thermometers, just records being broken all over the place. In the United States, where it was cooler, we didn't get so much the record hot temperatures, but we got a lot of precipitation. The cooling meant a lot of rain, and you probably saw all of the flooding that was in the news during during June and into July. Another place that has experienced a tremendous heating because of this is Greenland. This is Greenland. And in particular, it's been in the news a lot the last couple of days because with this present heat wave, there's just been record-breaking glacial melt in Greenland this last couple of days. And this graph is kind of sobering. The melt percentage has just been higher than the median by a long, long shot. The gray and the blue is sort of what's typical, and because of the very recent heat wave, it's just been gushing, quite literally. So this is sort of what it looks like in Greenland. That's all glacial melt, was ice and is no longer ice. And we've talked a fair bit about the consequences of losing massive amounts of ice out of the Greenland shelf. And how tricky that is for the kind of feedback effect of having the ice not be white, but large areas of it being not as reflective as ice and absorbing more heat. It's kind of a runaway situation. So that is very troubling and worrisome. Then we also pointed out the heat in Siberia. Siberia is having record fires. These is just an example of some of the boreal forest that is burning in Siberia. I forgot the number. I think it's something like 3 million acres worth of boreal forest loss. But in addition to the actual fire, there's also smoke, and this is just a NASA video that shows the smoke coming out of the wildfires. You can see and in fact, the smoke, because it's in the northern region, circulates around, and there's Russia, and you can see the huge amounts of smoke that have then swung around into Alaska and northern Canada. So it's a very devastating fire, and you've probably seen the headlines about the Arctic fires, plural, because there are fires really also in the boreal forests of Alaska and northern Canada as well. So this comes as no surprise. These are all individual incidents, but they are part of a larger trend, and these are this shows the June temperatures for the last 140 years. So it's hot and continues to rise. So when you start looking over long-term periods of weather anomalies, and those anomalies start to be the same year after year, that's when you make the transition from discussing weather into discussing climate. Now, one of the papers this past, I think it was last week, in Nature, examined whether or not this is different than heating trends in the past. And in particular, let me break down this idea of a globally coherent warm and cold periods. Just like the map we showed you of June, there were some places that were warmer, some places that were cooler. But when you average over longer periods of time, you can see that that trend holds up. Even if you look at a whole year or a year's worth, some places are warmer, some places are cooler, until very recently. So we didn't have really good measures of global temperatures all around the globe over what they're referring to as the Common Era, meaning since in the last 2,000 years. So this study in Nature took data from all around the globe, and you can see the yellow or the green and orange and blue dots, and up the top it says bivalve, meaning looking at historical populations of sea life, coral, glacier ice, and sediments, and used those data to pull out the temperature history around the globe and then look at it from a global perspective. And the short version is this is the result. If it's up above the line in pink, it means it's warmer, and below the line, it's cooler. And in particular, they show how much of the globe on any given year is warmer and how much of the globe is cooler. And what you really see through most of this is that throughout all of this period of the last 2,000 years, some places on the globe are warmer and some places on the globe are cooler, until you get to just the last several decades. So here's a kind of just a zoom in just to show you what I'm talking about. It's not like everything's all on one side, but when you come to the 20th century, everything has now moved on to the warm side. In other words, it's a globally, spatially coherent heating. Everything is heating around the globe, not just some places warmer one year and some places cooler. In particular, they talked about something called the Little Ice Age, and we've all heard of that, ranging from about 1300 to about 1850. And I didn't know this until I read this paper, but actually that happened in different places on the globe at different times. So in the 17th century, well, in the 15th century, it was more around the Pacific in that hemisphere. In the 17th century, it was more in Europe and Eastern North America. It was more surrounded around the Atlantic. And in the 19th century, it was more in the Southern Hemisphere and in other areas. So I always thought of it, because we always get biased by the idea of what we hear in Europe, the Little Ice Ages in Europe. And so that was what we know, because there were paintings of people skating on rivers and so forth during winter. But in fact, these global data show a different picture. Now, there is no puzzle as to why this is true. We now know full well that the carbon dioxide, the carbon that's being put in our atmosphere, completely correlates with the warming trend that we're seeing, and we've talked about that here quite a number of times. So I'm not going to go through the whole history about whether or not global climate change exists. It does. Warming does exist. And the term global warming, it means it's getting warmer, and it is, and that leads to climate change. So sometimes your people quibble over, is it warming, is it climate change? It's both. The planet is warming and the climate is changing as a result. So, of course, that is the input of carbon into the atmosphere that from the beginning of the industrial age to the present industrial age. I failed to mention that in that study about the global coherence, I see there's some questions, but if you can wait until after I finish, I'd be grateful.
Wondering whether you're being amplified and that whether or not you're going on your live stream.
Oh, is it not amplified? I hear amplification. Okay. Let's see. Oh, yes. I was going to say that the warming and cooling around the globe in different places is exactly what the models predict for what they refer to as stochastic weather and climate. In other words, random. It could be no matter how many times you run the models with that amount of carbon in the atmosphere, you'd get warming and cooling. It's just what you would expect. Some places warmer, some places cooler. But because now everything is warming, the real conclusion of that is that non-anthropogenic sources, in other words, before the industrial era, there were no forces that could drive a global change of the scale that we've seen since the anthropogenic, in other words, the human sources. So one of those issues that you often hear is, okay, the climate's warming, but is it human caused? And this study that shows it happening globally, unlike any time before in history, is a very clear indication that yes, it's tied to the anthropogenic meaning created by humans sources. So I said at the end of last year when I was talking about climate and said this is, we can't just always talk about the problems, we need to talk about the solutions. And maybe some of you saw in the news that there was a very optimistic study that said that by growing forests and growing a lot of forests, we can help abate global climate change. Now, we did talk last year about the fact that we're coming very close to a tipping point. We're trying to stay below a warming of 1.5 degrees centigrade. And because once you pass that, other feedback mechanisms like the melting of the glaciers or the melting of the permafrost come into play and drive the sources of carbon and the warming even higher and faster. Trees are sinks. They take carbon out of the atmosphere and give us oxygen, of course. And so that's why it's so important to have trees. And of course, that's something that is challenged at present.
Time in a tree?
Time in a tree. Excellent. Yes. Absolutely. And so, clear cutting happens. This is a picture in the Brazilian rainforest. So the last thing we needed to be losing trees, we need to be gaining trees. So there was a recent paper just published that talked about the potential for restoring trees. And I'm going to jump, two things. First is that they followed on work from 2015 where a guy, as part of his thesis and postdoctoral work, and worked with a team to count trees, and took over $1.2 million. Yeah, took over 1.2 million measurements around the globe and compared them to the traditional way of counting trees through satellite imagery, and was able to ground truth the satellite imagery. And what they found from 1.2 million data points around the globe was that there are in fact about 7 times as many trees as we had thought. There are about 4 trillion trees, 4.3 trillion trees, and we had thought there were only a couple hundred billion. So this is good news, more trees than had been thought, but he followed on this work with this team to explore, well, what's the potential? What's the tree carrying capacity? How many trees can the Earth support? So these 2 next graphs are what are results from that. The first shows and this is a result from their computer models, which were very sophisticated, using all these local ground truth data to develop, and they used machine learning, a mechanism to determine how many trees a given environment can support. So this is their result. How many trees can a given area support? These are not data of how many trees are there. This is a result of their study. And sure enough, the trees are where the trees are, right? You've got the Amazon, you've got the Congo, you've got the eastern United States. And so their model predicts very well the actual distribution of trees. However, if you take away the actual trees, you can see that there are lots of areas where there's potential to grow trees. And in fact, if you take away the urban areas or human use, land use areas, so cities, farmland, anything that people need land for, you still get enough land, about the equivalent of the area of the United States. And if those were planted with trees, then the sink can take away about 10 years worth of the global carbon budget that's been pumped into the atmosphere. So this was a very optimistic result. And a lot of countries are trying to do that just as we speak. Here, these are all Ethiopia, 200 million trees a day. Pakistan, Bronx is planning to plant a million trees. And here's just a picture showing a region that was ripe for planting trees but had been clear cut long ago. And then they planted trees, and now it's full of trees. And I think we all have seen areas that could potentially have this. There is a short video, it's about a minute long, that that their team put out. And I think we'll just take that moment, 9:15. Yeah, I think we have a moment. We can watch it. So two of the comments that they made on there was you would have to take too much land. But in fact, and it said his results are being reviewed for publication. They're published. That's the paper I showed you. So they're published now, and it's been reviewed. And as the results said, it's talking about land that's not farmland. So that criticism has been responded to. And the other was about water. Is there enough water? But in fact, when you grow trees, the soil holds the water better. And in fact, another video that's much longer, and we didn't choose to show tonight because it was too long, shows that when you reforest an area, actually the groundwater is enough to get even runoff, like streams form in areas where you've put trees, because you're not parching the land anymore with direct sunlight. You're shading it, and the water is being held in the soil by the roots. So it's a very hopeful idea, and maybe we'll all participate in a little tree planting. So with that, Patrick, you want to tell us a little bit about the spirograph?
Oh yeah, so if you enjoy scientific illustrations and infographics, this is a site that's worth going to. It's called Tabletop Whale, and it's created by a biology PhD student by the name of Eleanor Lutz. And there was one graphic in particular that I really liked, and she describes how it was created. And that is an orbit map of every object in our known solar system. So how would you create such a map like this? This is just a portion of that particular map among the other illustrations you can take a look at. And let's go to the next slide, and we can see just kind of the method that was used to create the orbit map. And we're going to break it down a little bit, and so we'll go to the next slide. Basically, what the student did was go to all the JPL and NASA databases and take all the orbital elements of large comets, asteroids, and moons and planets, and then basically clean up the data, because all the data is in different formats. So it was all cleaned up in a format that can be read by a program called Python, which is a program that people use even to program apps for your phone, for instance. And then you can generate from that data little data points called scatter maps, and then using Illustrator or Photoshop, you can assign different color values to it and really make an artistic rendition representing all the data from that program. So along the way, we can go to the next slide. She was able to say, well, I've got all this data. Let's have some fun here. So for instance, instead of saying, here's the sun, and then all the planets go around it in little concentric circles, let's put the Earth right in the middle, like in the old Ptolemaic days where we thought we were Earth-centered. And let's take Mercury, so the Earth's here, and kind of revolve it around the Earth so the sun would be here. And it would trace this beautiful kind of spirograph pattern, which I remember in my younger days playing with spirographs, like a cog and then just moving around with a pen. Mm-hmm. And you can see various patterns created by other planets, and so from Venus through to Uranus. So that's kind of neat. The other thing is, and we can go to the next slide, is how to deal with scales, because if you were to represent the solar system in a linear fashion, so you'll find out that most of the objects in the inner solar system are all bunched up near the sun. So a way to solve that issue is to kind of stretch them out using a logarithmic scale, which you see at the bottom there. And so you take all these planets, which were all squished up, and now they're all spaced out evenly. And then for your distant objects, your planets are kind of a little squished down on the logarithmic scale. The other thing was you can represent your orbits in different fashions. For instance, this is a orbit ribbon where you can take a year's worth of a revolution and have orbiting objects going around it, like that. And of course, this is the traditional orrery type of orbit that you can do. This one is a crazy, looks like a Lazarus figure, or you see on oscilloscopes and something like that. So I don't know how that was created. And this is another representation of an orbit ribbon with a lot more objects. So what's the end result of all of this? Well, it's this beautiful graphic. And it's so dense, and there's so much information. Here's the legend. So you might want to go to the website. This is the website. And take a look at this. This represents positions of all the solar system objects as of New Year's Eve in 1999. So worth taking a look at. Yeah.
So our next, our next story is actually a one I covered last month. Did kind of a poor job on it. The earthquake rattled me, so to speak. And I wanted to get on to the next part about the black hole image. This was supposed to be a lead into it. But I went back and looked at the story. It was super interesting, and it ties into other stories I'm going to tell you this month. So very briefly, what they did is they looked at the very center of that galaxy. It's a dwarf galaxy, and they were trying to measure the mass of the black hole. They were looking at the clouds of gas orbiting around the black hole, but very close to it. Now, those clouds travel quickly, so they're moving around very, very fast. Light from the black hole comes off, bounces off the cloud, and hits the observer. But some of the light went straight from the black hole to the observer. So there is a time delay from the light that bounced off the cloud and came to you. They use that time delay to figure out how far away those clouds are orbiting from the black hole. And then they also use something else called the line width of the broad line region. You see where it says BLR. These clouds themselves also give off light, But because they're traveling so quickly, some of them are heading towards you, some are heading away from you, the Doppler shift spreads that light out into broader colors. So the narrow lines are coming from clouds that are quite far from that picture. They're further out, and they're not broadened by that Doppler result. So you can use that, well, you need to subtract it out. First of all, they use these other lines over here to make a model and subtract out that narrow part in the middle, and you're left with a broad region in red. And the width of that is an indication, along with that delayed time, you have to actually use both of them, it gives you the mass of that black hole. And it turns out that black hole only had a mass of 10,000 suns. Super, super small. That's incredibly small. The one in the center of our galaxy is 4 million solar masses, and ones that are supermassive are up in the hundreds of millions of solar masses. So this one at 10,000 is a rather small one. However, it falls right on line for a dispersion relation where the speed of the stars and the bulge of the galaxy, their spread tells you the mass of the black hole, and this one falls right along that relation, so it's kind of interesting. Now the Hubble Space Telescope was used to look at another galaxy, this one NGC 3147, and they peered deep, deep, deep into the core, and they discovered that it has a disk buried really close to the black hole. How did they do it? Well, again, they used those broad lines and narrow lines. So looking again, this is a spectrum, so color is sort of left, right, and brightness is going vertically. You see these narrow lines in the middle. Again, they can look at those and subtract them out, but then they had this very broad region here. Now this is much broader than in the previous case. You look at on the left, notice the numbers here, the spread, we're going from 65040-ish over to 6600. Over here, 6400, all the way over to 67. So, I mean, the spread is incredible on this. They had looked at this galaxy before, and they had never seen a broad line region on it because they were probably zoomed in too far. If you're only looking at this middle part here, you think it's flat. They had to go much further out. Now, there's another weird thing in this one. Notice it's asymmetric. The peak on the left is taller than the peak on the right. That's a sign of relativistic beaming. If you remember that black hole image I talked about last month, part of it was brighter on the one side and it was dimmer on the other side due to the spin. Same thing you're seeing here. That disk is moving fast towards you on one direction, and relativistic effects, stuff Einstein taught us about, brightens it. So that's the reason that the red is peakier on one side and not as peaky on the other. So this tells them that disk has to be super close to the black hole and going really quickly. This black hole, by the way, has a mass of about 310 million solar masses versus the 10,000, so different beasts. They expected sort of a puffy donut around it. They didn't expect a disk down inside. Now why? Because it's not an active galactic nucleus. It's not currently in a quasar form. When a black hole eats, a supermassive black hole like this, when it eats a snack, when matter falls down into it, you get a lot of radiation out of it. It glows very brightly. We don't see that here. So we thought it would be sort of in a quiescent phase where you have a very thin sort of donut of material around it that's just hanging out. Instead, they see a very thin disk, very, very close to the black hole, which was unexpected because this isn't glowing. So why is this not feeding? Why is this material not falling in and creating a quasar, creating an active galactic nucleus? We're not sure. It might be the case that this was thought of as a class of galaxies called a Seyfert II, where we didn't expect to see this disk down in there. Now they're starting to question whether all Seyfert IIs might have a disk down in there, and we need to study a little bit more about why it's there, how it's there, and maybe we've just missed them because we were looking too narrow. We needed to broaden our view to see the full broadline region. At least that's one of the things they're thinking on this one. Now another story that ties into it is about the alignment of the disk, the accretion disk. That's material that's falling in on the black hole and spiraling around it can form sort of a pancake around it. Well, notice in this illustration you see one that's tipped and a disk on the outside. And this is a prediction from general relativity, and some folks have done a general relativistic magnetohydrodynamic simulation. So is everybody ready to go back to school and do one of these? What that means is they're looking at sort of how the gas is behaving like a fluid. It's dense enough, it moves like a fluid. They needed magnetism to describe it, and they needed Einstein's general relativity equations. Well, I'll just show you the simulation here. Now notice the disk out here let me restart it again, and I can wait quicker. The disk out here is at a different angle than the disk in the middle, and you can see over time it flattens out. It becomes much, much flatter. This is a zoomed-in view, and this is a further out view. And what's happening is that inner disk is aligning itself with the spin of the black hole. The black hole itself has a spin, and there was a prediction that due to effects of space-time itself around the black hole, don't have time to go into it, it would take months of lectures probably to describe it all, but needless to say, this simulation is the most accurate simulation, the most detailed simulation of a thin disk near a black hole. And they could even torque it this much, and that disk slowly aligns itself. Again, they're keeping the middle disk horizontal, and they're letting the outer disk realign. Now, one funny thing is the outer disk actually will realign via a different non-general relativistic effect over time. They also were able to show, and extra cool, they were able to show how jets get created around these. The thin disk comes in and interacts with the magnetic fields, interacts with the gravity and everything else. And these lines they're showing here are lines of constant magnetic field. So the material is literally funneled up and down out of there, and it creates the jet. So they're able to create a jet with this as well. So these simulations have come a long way, and observations are coming a long way at the same time of these black holes. So it's an exciting time to be studying the material down near the event horizon of a black hole. We're starting to get close to that level.
Is that related to frame dragging? Or?
Absolutely. Okay. Yep. It's all frame dragging that causes this. So, and that's the space-time itself, the fabric of the universe, is sort of dragged around as the black hole spins. So some very weird effects happen down in there.
That was epic.
Yes, it's time for the SpaceX
it
report.
It is indeed. So what's SpaceX been up to? Well, on July 25th, after a one-day weather delay, Falcon 9 mission called CRX-18 launched, and it's a resupply mission to the International Space Station. The 18 refers to the 18th launch of this type. 9 minutes later, the Falcon 9 first stage landed successfully in landing zone 1. You can see there on the right. And then 2 days later, the cargo ship, the Dragon supply ship, arrived at the space station. We see some video of that somewhere. There it is. And there it is with a strobe light. And you can see the little grappling thing there. This is the 60-foot arm that basically grabs the supply ship and then attaches it to the space station so it can be unloaded. It's going to stay there for about 4 weeks, and then we can go to the next slide, because what's inside of all of that? It carried about 5,000 pounds of payload, and there's equipment in there that can support up to 250 science experiments on board the space station. This next one is a fun one, because the crew decided to take a selfie with the ship, the cargo ship in the background. And this isn't the first time this cargo ship has been to the space station. In fact, this is going to be the third time, April 2015, December 2017, of course, last month. So let's see, that's...
Just before the show,
yes,
is they actually painted little space stations on it for every time they've docked.
That's an excellent observation.
Oh.
I was circling.
Oh, okay.
Oh, there it is.
Right
yeah.
there.
That's 2. So the next one we'll have another one.
That's great. Well, at the same time, SpaceX was doing another first, and that is with their Star Hopper. Now, it looks like a water tank, but in fact, that is a prototype spacecraft that's under development. And several months ago, they did what was called a tethered test, a static fire. I guess that was just, oh, wow, that was just July. Phew. That felt like months ago, before Apollo. And so they just fired the engines. They didn't go anywhere, but they just fired it. It was tethered, so it was a static test. So then they also had a delay. They tried to go on the 24th, but in fact on the 25th ran a test. And here you can see it actually gets off the ground. there it goes. Before it gets completely covered up by smoke, it was taken at night. The test of the day before they had broadcast live, but then they didn't broadcast this one live. The day before it was not successful. They had an overpressure in the one of the tanks, but this one was successful. And here's another view of it. This one's taken from a camera that is under the star hopper and looking right at the rocket, so you can see the ground receding away, and it kind of moves a little bit laterally and then sets itself back down. So Elon Musk did tweet, "Water tanks can fly," and so there's a lovely picture of the venting.
Do you know what the purpose of the star hopper is?
As a matter of fact, the purpose of the star hopper is to make life interplanetary. It's part of a long-term strategy because it's a much more powerful rocket. It's based on methane and liquid oxygen combusting rather than kerosene and liquid oxygen, which is the Falcon engine, Merlin, I think it's called. So the idea is that this rocket will take us places like the moon and onto Mars. And so, in fact, this is artwork of what those rockets will eventually look like, and just as a reminder, this is where we are now. But every journey has a first step, so it got off the ground and it landed safely, and this is a big step forward for their Star Hopper project. Now, I am going to race through some stuff about the moon. We had put this in here just in case we thought maybe the show was running a little short. So you won't miss much, but I'll give you the headlines. First of all, isn't that a pretty picture? I took that with David Pinsky, who's often here, and I don't think he's here tonight. But the two of us went out and snagged that picture. We were pretty excited about it and the only reason we could get it all, this is not a composite or anything, is the moon is behind clouds, so the clouds kind of dimmed the moon enough to make it the same brightness as the observatory. But anyway, the moon is beautiful. Then I was going to talk a little bit about how it was formed through a major impact that put a big ring of debris around the Earth that then came together and formed the moon. And I'll just show the start of this animation because isn't it fun to watch the Earth turn all glubby and get distorted by this impact? But you can see the stuff that's around it. That all falls in eventually to the moon. And there are a couple of observations many observations that are consistent with this picture. One is the size of the core, which is tied to what David was talking about earlier with regard to how quakes progress through the Earth versus the moon, because you've got a much smaller core on the moon, and that's what you would expect from that collision. There's also kind of a cool thing where the rocks that came back from Apollo have much the same composition, really suggesting that the rocks of the moon came from the Earth. And there's a lot of data there to show that. And here's another moon rock. But there was kind of a cool result as well. One of the ways in which they're different is that there is not quite as much sodium or potassium in those rocks. And it's not because they haven't had enough electrolyte drinks, but
Need a banana?
It needs a banana. But anyway, sorry, Patrick.
Sorry.
And I should have said
right.
methane. What's wrong with me? But anyway, one of the stories, one of the kind of cool results from this past month is that a scientist at Goddard Space Flight Center, a NASA lab in Maryland, did a little analysis that said you could get rid of the potassium and sodium by having solar activity just come in and basically knock it off the surface of the moon. And the amount of solar activity is tied to how fast the sun is rotating. So it kind of dialed back, like tried to extract backward to how fast the sun was rotating in the early ages of the solar system. And in fact, this says that the sun was not a fast rotator. It was kind of a slow rotator and not as active as a fast rotator would be. This is important because life on Earth started pretty early in the solar system, and if we had had a very, very active sun full of flares and solar storms and coronal mass ejections, it might have been more difficult for life on Earth to form. The reason we did the story was really to show you this video. This is sodium thrown into a lake. So everybody likes, we had to show you that video of sodium and how it reacts. But moving on, another story from the past month was that there's this very major crater near the south pole of the moon called the South Pole Aitken Basin, and measurements were taken from a pair of satellites called GRAIL, which measures the gravity of that region, and determined that there's in fact a tremendous amount of gravity under this thing. So one of the possible explanations for the fact that not only is there a big, huge basin there, but it also has a heavy tug, and there's some mass under it, might be that whatever was left of the asteroid that crashed in that created this basin, which happened very early in the moon's history, shortly after it was formed, might actually still be present and be responsible for that gravity. Then the last little bit to share is that we put bases on the moon this last month. You probably didn't know that. Not true. That was a lie. But if we're going to do it, we need water. We have to have water because we can't carry our own water. So you want to get water out of the lunar soil. So a little spacecraft called Chandrayaan-1 in the late 1990s mapped the entire lunar surface and found evidence for water ice in craters. And here's a nice little map of the blue parts where it is on the moon. And this was the start of a whole idea that maybe the moon isn't as dry as we thought it was. Maybe there's a lot of water. Then the United States, NASA sent up a mission called Lunar Reconnaissance Orbiter that had a little thing on it called L-Cross, which basically was an upper stage of a rocket that they crashed into the surface of the moon, spewed up a plume of lunar material, and measured, yes, water lines, emission from water. So it's really quite well understood now that there is very likely water. How much we really don't know, but water at the poles in what are called permanently shadowed craters. So as you can see, as the time goes on and the moon moves in comparison to the sun, goes through its lunar day, which is 28.5 days, there are craters on the south pole and the north pole that never see the sun because the shadows are so long. And it's thought that, in fact, there's quite a bit of water. This basically does the same thing, but then overlays data that shows water ice. Last month, we talked a little bit about Chang'e 4 that has gone to the South Pole Aitken Basin and sending us back information. But this past month, there's a new headline of a mission to the moon, and that is Chandrayaan 2. Remember, Chandrayaan 1 made such a great contribution. Successful launch.
Plus 5 seconds.
दोनों का प्रज्वलन हो गया है और उससे 640 टन वाले मार्क 3 रॉकेट नौगन को ऊपर की ओर लेके जा रहे हैं.
And in the interest of time, suffice to say it got to orbit. It's just great. They have made the maneuvers they need to make, getting it in a higher and higher orbit to take it to the moon. I'll actually dial back here just to show you it has a little tiny rover on it as well. And it is going to the lunar south pole. So that is the plan. I'm not going to take the time to show these animations. Suffice to say, the little mission will eventually get to the south pole of the moon. And the animation, whoa, there it goes, caught. And so it is captured by the moon and goes to its south pole.
Where was it launched from, please?
Where was it launched from?
Ghana.
India, right? Ghana?
Guyana.
Guyana?
I think, isn't it?
Okay. Where was it?
This is Eastern Launch Center. That was in India.
In India. Oh, it
in
was
India,
India. Okay. So with that, cool thing, we keep watching that mission because it's really going to tell us a lot about the South Pole and whether that can be a future habitat for us.
All right, so I'm going to go quickly with this. On the day of the 50th anniversary of the moon landing, July 20th, for Apollo 11, the spacecraft Juno passed close to Jupiter, a mere 2,600 miles at its closest point, known as Perigeo. This is its 21st time it's done this, and it flew, as you can see here, close to the Great Red Spot and was able to take some pictures of it. So we're going to show you these images of the Great Red Spot, which is right here. There it is, and taken from a distance of 26,000 miles. We'll just go to the next slide, and here's another view showing the Great Red Spot and the southern hemisphere of Jupiter, and a very detailed view of the red spot. Now, this is not the first time it's been to the red spot. It's flown over twice before, and you can see some changes. Here's some material coming off of the red spot, and 5 months later, it's all gone. In the next image, we see the northern hemisphere of Jupiter with these kind of swirly storms, and then notice this kind of brownish area. The next slide, as Juno moves over, it reveals this gigantic barge, we call it barge, but it's basically whipped by winds like jet streams. Next slide, some detailed views of storms, and this is the last one is one of the best I've seen of one of Jupiter's storms. This one is called the swirl. And remember, all these images are color enhanced, so they're actually pale in color if you actually look at them with your own eyes.
Amazing. So in our final story, I believe, final space story, this is an image of the Milky Way as viewed from Earth. And the telescope's a little blurry because those domes were moving, and yes, we shoot laser beams at our galaxy. But this story isn't just about that. It's about the neighborhood of the Milky Way, and this is a view, sort of an external view, artist's conception of what we think it might look like from outside, and there's that bar there. Neighboring galaxy of ours, M31 Andromeda. We make up a local group. It's sort of our local neighborhood. There's a lot of dwarf galaxies there as well. Andromeda's close to us. Well, we want to know even what's further out there. What if we walk a little further in our neighborhood? Well, you run into the Virgo cluster. We have that image on our big picture, just in the depths of space. And here's the map of sort of where we are. If the Milky Way is in the center here, where do we go? Here we go, local group. Here's the Virgo cluster. Well, I've lost my way here. Anyway, Virgo cluster is the nearest cluster to us. It's about 50 million light years away from us. It's on the right-hand side. Yeah. I'm seeing it now there. So this, again, is super close to us, but we want to know even more. Well, some folks that studied, they predicted that all the local galaxies would flow together into a supercluster, did a study that I'm going to tell you about. But first of all, when we look to the north and south, we can map out galaxies using a method to get their distance. If you use the redshift, you can get a distance out of that, and you end up getting these weird sort of concentrations of galaxies in regions with underdensities, and they call the underdensities voids. More and more surveys were done, as you can see, covering more and more area. Well, why did they do slices like this, and why do they avoid certain directions? Well, it turns out that our own galaxy gets in the way. If you imagine this is a side view of our galaxy, we're located somewhere out here. Well, you can look up and down easily because you're not looking through much material. But looking anywhere along this disk direction, there's too much stuff in the way. You can't see there. It's called the zone of avoidance. So the surveys can only look up and down, really. Well, to map out what is in that area we can't see, we can use the motions of the galaxies and the directions we can see. So you can take those galaxies, figure out how far they are away, and then put them into motion and say, let's let their velocities tell us something about what is tugging on them. So you plot out the direction they're going to be going, and you look at their instantaneous velocities, what they're doing now, and you can kind of figure out what could be pulling on them. And it turns out right next to us, this was done back in 1987, there's a local void. There's actually a kind of one of those holes in space where there's an underdensity. The Milky Way is right on the edge of it. Well, the new work they're doing now is mapping this void out in greater detail. So you fast forward 30 years and they're starting to get sort of a lot more details about it. And here's what they found using all those velocities and motions. They've just measured the speeds and directions of many, many, many more galaxies. And this is sort of what it looks like. The deep red is where there's lots of stuff, and they now have colored in black the local void next to us. And it's about 50 million light years in one direction, 60 million in another, and about 70 million in the third direction. So it's sort of an oblong shape. They're starting to get to the shape of the local void. But who knew our Milky Way was kind of out in the boonies, really? We're right on the edge of it. You go for a walk, you'll get lost in this void out there.
All right, so to conclude this evening, we want to remember two people who passed recently. So Patrick, you want to tell us about?
Yes. So Christopher Columbus Craft was NASA's first flight director, and he passed away on July 22nd, just 2 days after the 50th anniversary of Apollo 11's moon landing. He was basically credited for as a foundation of building up mission control. So its organization structure, its whole culture, and how mission control should be. So he was there for the first missions, the first crewed missions, including the Mercury Redstone launches in the early 60s. That included the launch of the first chimpanzee into space, Ham, and the first orbital mission, human mission, which was John Glenn, and the first spacewalk in 1965, Ed White. So he built up that mission control to what we know today, and mission control, and he also hired, for the Apollo era, Gene Kranz, who was well known for his failure as an option. So these are the type of people that are really needed in mission control, people that can work under pressure and have no egos themselves, and be able to do the work and make the hard decisions.
And the other person that we lost this year was Murray Gell-Mann, and we failed to talk about this earlier. He's a physicist and a Nobel Prize winning physicist who is known for his work in many, many studies related to elementary particles at a time when particle physics was really just coming into existence and coming into full blossom. He's probably best known because he is one of two physicists who independently came up with the theory of quarks, that atomic nuclei, that protons and neutrons are actually made up of smaller particles called quarks. And he's the one who coined the term quark, which is from Finnegan's Wake, James Joyce novel. So there we have his quarks in plushy form, and of course a picture of him. He was sort of an irascible fellow, very demanding on himself, spoke many languages, gave the last part of his Nobel Prize acceptance speech in Swedish. But we liked this quotation from him: "If I have seen further than others, it's because," and you've heard this quotation before, because you've heard it as because I've stood on the shoulders of giants. His version of it is, "If I have seen further than others, it's because I'm surrounded by dwarfs." So that gives you a little sense of Murray Gell-Mann. But he was a devoted mentor to many, and a brilliant physicist, and he will be missed. So with that, we have a little walkout music for you that will remember a non-physicist, but someone that we thought we would honor who passed just this week, Hal Prince. And if any of you like Broadway musicals, you know who he is. But with that, we'd like to just once again remind you that our next show is on September 6th. We hope you'll come back, hear all about the James Webb Space Telescope. And we thank you for coming, staying, paying for parking, and being here for tonight's program.